Well, it looks like it's time to get started. So hi, everyone. Welcome to this week's iteration of the PALS seminar. So this week we have Temitope Jaiyeola here to speak to us about a study of non-associative hyperstructures and algebraic analysis of selected physical systems. So please take it away.
All right. Thank you so much. Let me appreciate the organizers for this great opportunity to share my work with fellow scholars. The title of the work is Study of Non-Associative Hyperalgebraic Structures and Algebraic Analysis of Selected Physical Systems. It's the joint work with Oyeyemi and Ilori. This is the outline. We'll take a background on algebraic hyperstructures. I will introduce two particular physical systems, the leptin group and some chemical reactions, disputation reactions to be specific. I'll take a literature review in historical background of hyperalgebraic structures. Then we're now going to the motivation for the problem at hand. Then the results will be presented. Hyperalgebraic structures were introduced by Marty in 1934 during the 8th Congress of Scandinavian mathematicians. And there she introduced the notion of hypergroup. And the motivating example for this is giving a group G with a subgroup, which is not necessarily a normal subgroup. If you consider the set of left cosets of K in G, then with the usual composition, you can build that factor set into an hypergroup. So hyperalgebraic structures, they are generalization of well-known classical algebraic structures such as semi-group, groups, and some other non-associative structures such as quasi-groups and loops. And they have found application in diverse areas, name them rough set theory and the likes. And so definition of terms, if you have a non-empty set H and you define an operation on it as follows, from the Cartesian product of H with itself into the set, the power set of H exempting the empty set, then the pair H and that binary operation becomes what we call an hypergroupoid. So if an hypergroupoid possesses the associative law, then it has to satisfy that condition. The reproduction law axiom is as given, and the existence of identity, that is, if for all x in H, x belongs to the hyperoperation of x and E and X as well. It must be noted here that unlike in classical algebraic structures, where the composition of two elements gives just a single element, in the case of hyperalgebraic structures, it gives you a non-empty set. Okay, and so this leads us to some new hyperalgebraic structures from an hypergroupoid. If an hypergroupoid possesses associative property, it becomes an hypersemi-group. If an hypergroupoid possesses the reproduction axiom, becomes an hyper-quasi-group. And if in addition it possesses the identity property, as earlier on stated, it becomes an hyperloop. And if an hyperloop possesses the associative property, it becomes an hypergroup. And of course, an hyper-semi-group that is also an hyper-quasi-group is an hypergroup. So here is an example of an hypergroup from a group, given a group G and a subgroup of G with the factor sets as defined. If you put a binary operation, if you put an hyper operation on G slash H as given, as defined there, it's your G, comma self will become an hypergroup. There have been several kinds of hypergroups that have been introduced in literature, such as regular hypergroup and the rest. But here we are concentrating strictly on arbitrary hypergroup. Then we also have some weak hyperalgebraic structures, which are generalization of algebraic hyperstructures. They were introduced, they have been studied by Jospy, Davas, and some other authors. One of them is if you an AG group and an AG semi-group, and AG group are good examples of weak hyperalgebraic structures. Weak in the sense that the associative law does not necessarily need to hold, does not necessarily need to hold. So in this case, we call this the weak associative law. That is, the right-hand side and left-hand side of the associative law might not necessarily coincide, but they could intersect at some given point. We also have the weak commutative law as well. And this is a chart that relates the weak hyperalgebraic structures. If you have an hypergroupoid with the weak associative law, that is the WAS, it becomes an HV semi-group. If an hypergroupoid possesses the reproduction axiom, it becomes an hyperquasi group. And an HV group is an HV semi-group that has the reproduction law, while the reproduction axiom, while an HV group is also an hyperquasi group that has the weak associative law. Now we come to some other hyperalgebraic structures that are actually weak. These were introduced by us. Given a polygroupoid, given a non-empty set H, and three hyperoperations, dots, the right division, and the right division and the left division, and you also have a unitary operation. So you call H under dot a polygroupoid, and whenever a polygroupoid possesses the following axioms, Roman numeral 1, 2, 3, and 4, you have some new hyperalgebraic structures. A polygroupoid that obeys Roman numeral 4 will give you a polyquasi group, and in addition, a polyquasi group that possesses Roman numeral 2 will give you is a polyloop, while a polyloop which in addition obeys Roman numeral 1 will give you a polygroup. So you can always from here see a polygroup as a generalization of groups. For instance, if you critically look at this is associativity, extents of identity. If you restrict, if your hyper operation becomes a binary operation, if you restrict it to be a binary operation, then that third axiom takes care of existence of an inverse element for each element in that particular structure. So that takes you back to our binary system. Here's an example of a polygroup giving a group G with a subgroup H. If you define double slash as follows, that particular family, and you put a star operation, hyper operation on it, then the algebra of double cosets will give you a polygroup. Here is an example of a polygroupoid. This will, without underlining sets, and an operation dots as defined, given by this particular multiplication table, is a polygroupoid. In fact, it's neither a polyquacy group nor a polyloop. This is an example of a polyquacy group. It is, however, not a polyloop. Later on, we'll see one of our results which actually characterizes polyquacy groups and polyloop. That is a way in which you can quickly check from the multiplication table whether structures of this form are polyquacy groups or polyloops. Here is an example of a polyloop. The underlining set EABC with these three hyperoperations as given in the tables here. So you have a polyloop. The standard model, the leptin, they appear to be structureless algebraically, okay, but they are made up of first generation, second and third generation leptins. And it has been established that they actually form, going by theorem 1.1, they actually form an HV group. So it will be interesting to know what weak property do they possess. It's a set that is made up of 12 particles as given there. And this is the multiplication table for the leptin group. It's an HV group. And this is, now we go on to some chemical structures, which have been shown to exhibit hyper-algebraic structures. The first one is the dismutation reaction for 14, which is as given in this table, is an hyper-algebraic structure. For indium, this is how the dismutation reaction, as an hyper-algebraic structure, this is how it looks like. And for vanadium, this is how the table looks like. So we'll be using some of our weak associative laws to get to know more about these structures as we go on. This is just a review on hyper-algebraic structures. Just like I said earlier on, the study started in 1934 by Marty, and several authors have worked on them and also applied them. For example, Davas et al. 2011, 2012, and co. studied the application of HV structure in chemistry and biology, and also provided a physical example of HV structure associated with the leptin group, the one I just referred to now. And up to date, people are still working on them. Okay, so the motivation for this study is actually the weak associative condition, which is the WAS. That is the fact that the right-hand side and the left-hand side of the associative law, even if it's not equal for all elements, it is not, the two sides are not necessarily disjoint. Okay, so, and the justification for this is the fact that by non-associative algebraic behavior, we are trying to check the non-associative algebraic behavior of some of the physical systems that have been identified to be HV groups. Two particular ones, the elementary particle physics leptin group, which I talked about earlier on, they form HV group. And there is also a super set of it, which is the H-boson, and some dismutation reactions. So the main problem is to precisely measure the level of weak associative condition when the two sides of the associative law are not equal and they are not contained in one another. So we want to measure, do a measurement of weak associativity using some weak associative properties. And so the objective is to develop a method of construction of polygroupoid, polyquacy group, and polyloop using groupoid, quasi group, and loop Then also to apply the obtained properties of the Kuratowski closure operator induced topological spaces in investigating the precise measure of non-associativity of weak hyperalgebraic structure, which some physical systems represent. Our results now. This theorem tells us that whenever you are given a non-commutative groupoid quasi-group of loop, okay, if you define an hyperoperation O dots on G, define an hyperoperation O dot on G as follows, and you introduce two other hyperoperations, this and this, in the following manner, then your G under O dot is a polygroupoid, G under the 3 is a polyquasi group, and G under the 3 with respect to the identity elements of the loop is a polyloop. And using this particular theorem, we have the following example. Example 5.1 is an example of a polygroupoid. Table 8 represents a groupoid. And with the aid of that table now, using theorem 5.1, which I just stated, you have table 9, which gives you a commutative polygroupoid. Another example here is that of a polyquasi group. So again, given a non-commutative quasi group, if you consider a non-commutative quasi group given by table 10, table 11, and table 12, okay? You are going to have using theorem 5.1, okay? You are going to get a polyquasi group as shown on tables 13, 14, and 15. And here is an example of a polyloop. Given a loop as shown in table 16, then using theorem 5.1, you can show that you are going to have, then based on that theorem, you will have a polyloop, okay, as shown in table 19, table 20, and table 21. The tables represents the 3 hyperoperations. So we now go into the equivalence of hyperalgebraic structures. If you can recall, I introduced some hyperalgebraic structures along the line, hyperquasi group, polyquasi group, and so on. So this theorem tells us when those that are equivalent amongst them. All right. And this corollary 6.1 is a very important corollary. Important in the sense that with it, you can tell by merely looking at the multiplication table of a polyquasi group or a polyloop, finite ones for that matter. That is, merely looking at the multiplication table of a finite hyperalgebraic structure, you can tell if such hyperalgebraic structure forms a polyquasi group or not, or polyloop or not. In loop theory, for instance, it is well known that for finite binary system, a groupoid of this sort, okay, forms a quasi group because no entry repeats itself in any of the rows or columns. In any of the rows or columns, okay, so this is a quasi group. It's not only a quasi group, as you can see, the entries in the border here, okay, appear in the same manner under element 1. So that means 1 is the identity element in this particular case. So for polyquasi group and polyloop, this particular corollary gives us a characterization. The importance of this corollary is that it gives us a characterization for polyquasi group and polyloop, just like you have them for binary structures. And the characterization in this case is that for it to be a polyquadratic group, the union of entries in each row and in each column of the multiplication table is equal to the underlying set, or every element in the underlying set is contained in at least one entry in each row and one entry in each column of the multiplication table. That is, for example, this particular table, finite algebraic structure, represents a polyloop. It's also a polyquadratic group. Why? Because as you can see, if you look through each row and in each column, if you take the union of the sets in each row and column, you are going to have the underlying set, 1 to 6. And as you can see here, okay, so 1 is playing the role of the identity element. So we move on now to what we call the nuclei of a polygroupoid. We have what we call the nuclei of a loop and of a quasigroup. Quasigroups and loops are not necessarily associative, okay, but a group is a loop or a quasigroup. So here we show in this lemma that the left, middle, and right nucleus of a polyquadratic group is actually closed, okay? So, and we need this for the Kuratowski closure. So here we came up with considering the power sets of a non-empty set P with a left nucleus that is not empty. So we were able to define an appropriate Kuratowski operator, and consequently show that it obeys all the Kuratowski closure axioms. And with this, we're able to build a topology on that particular set. We'll be using this in our investigation as we go on. We also check the continuity, but okay, then some interesting sets as well. Well, this is not really what I want to. Now I go into the analysis of the weak associativity in some HV structures. So we'll be looking at the first one we'll be looking at is the dismutation, so we are motivated to, first of all, before we can do our analysis, we started to introduce the nuclei of elements. Given a polygroupoid, we define what we call a left nuclear element, and is as given here. And we also define what we call the probability of a left nuclear for an element to be left nuclear in a groupoid. And for the left, and we're able to show that the probability of a polygroupoid to be left nuclear is as expressed here. So we did it also for the middle and also for the right, because there are 3 of the nuclei. Okay, so thereafter now we also introduce 3 other non-associative properties or weak associative properties. Flexibility, adopting flexibility, we're able to define what we call a flexible element, and its definition is as given in definition 7.13, and the probability of an element being flexible as shown in definition 7.14. 7.14, and also we introduce left alternative elements, the lap of an element X in a polygroupoid, and as well as the probability of an element being a lap element. as well as the polygroupoid itself, definition 7.19, being lap itself. And we also use that of the wrap as well, right? Alternative property and their probabilities as well. So using this, we're able to come up with some analysis. The first one here is algebraic properties and probability of elements in disputation reaction. So the analysis of disputation reaction for indium is as given. As you can see from this particular table, you will see that out of 9 triples in all for indium, had 8 triples that was nuclear for 8, okay? Indium plus for 7 and indium 3 plus for 8. And you have the others. And when you do a very good comparison, you will see that in all of them, it is only in the case of flexibility here, in which you have all the indium elements in the indium's reaction involved in indium, in which you have them to obey the flexibility law, that is, they are flexible. Okay? So the probability for, in all, as you can see, the probability for flexibility gives us 1, all true. All right? For vanadium, in case of vanadium, what you have is, as you can see, it also behaves similarly compared to indium. The behavior in vanadium is also similar compared to that of indium, as you can see here, flexibility. Okay? The highest probability, if you compare all the nuclei, at least the left, the middle, the right, their probabilities are less than half. And for the lap and the wrap, only V2 plus, V3 plus, and VO2 plus have probabilities that are greater than, as well as that are greater than half. Okay. Overall, for the structure itself, okay, for the hyperstructure, it is flexible. Okay, it's flexible, and only in these 2 cases, the lap and the wrap, does it have probabilities that are greater than half? For the other 3, as you can see, they are less than half. They are less than half. So 14, this is the output, okay? The probability for 14 is as shown here. And as you can see, just like we had it for flexibility, it was 1 all true. So, but if you compare for the elements or the hyperalgebraic structure, so you can see that we have probabilities that are greater than half here. Okay. So this seems to have more probabilities that are greater than half compared with the last we looked at. Okay. Okay, so you can now do a comparison of the three hyperstructures, sort of, based on their, considering their probabilities. So as you can see, the three of them, the three of the hyperalgebraic structures, they are all flexible, okay? Even though they are not left, right, or middle nuclear, and they do not have lap and wrap, but we can see that amongst all these, the indium has the highest probabilities, okay, compared to the tin and the vanadium, okay? Even though for the lap and wrap property, the probabilities are the same for indium and tin, while that of vanadium is the least. So yeah, just some discussion, some of the things I've talked about earlier. Now if you take the Kuratowski, consider the Kuratowski-induced topological space of the hyperstructure indium, we discover that the topology contains only the empty sets for indium. So that's for the left, based on the left nucleus. For the middle, it contains 3 elements, and for the right, it contains only the empty sets. So we can see that in this case, for the right and the left, the topologies, for the right and the left nucleus, the topologies are the same. Okay. And you can also do the elements of the leptin group, okay? If you consider their left nucleus, right nucleus, okay? Their flex, the wrap, and the lap, you have the following outcome. These outcomes you are going to have. And, okay, so you see the same algebraic structures. Algebraic structure, we are just using, for convenience's sake, we are just using ABC to represent them. And if you consider their probabilities, this is what you are going to have. Okay. If you consider, for example, this particular element A, okay, which is this, has 1 all through the probability relative to all the properties, the weak associative properties that we consider is 1 all through. Okay. For these elements, you just have this to be 1, just this one in this instance. You have these 3 and you have these 3. Okay. So, and the properties of the others are also given here. H, as you can see, there's another element here that has a probability of 1 all through. Right. And we have to believe that these observations probably have some chemical reaction interpretation, sort of. The left, right, middle, and right nuclear Kuratowski-induced topology for the leptin group is as given. The one for the right nucleus is this. The one for the middle is this. And for that of the right, it's just this. So in conclusion, in this work, it was discovered that polygroupoid, polyquasi group, polyloop can be constructed using groupoid quasicles and loop. And in this study, we discovered that the hyperalgebraic structures representing this mutation reaction for indium, vanadium, and tin is non-associative hyperalgebraic structure. Even though in the dismutation reaction, indium and 2 of the elements exhibited high level of being nuclear in the right, left, and middle based on their probabilities in this respect. it was concluded that the structures form dissociation that form dissociation reaction has flexibility property, and we got the work published this year. So these are my references. There are some of the references of the work. All right, thank you so much.